Hey guys, your boy Chili here. Welcome back to C++ multi-threading. In this video, we're going to solve our problem of unbalanced workloads with a little queue, a very simple queue that is going to change the way that the tasks are allocated to our different workers. Just a quick recap. We started with a setup like this where we had one array per worker thread, and in every chunk of work, it would just work on a fixed span in that array. And then we changed that up a little bit when we started doing measurements. We reorganized our data, so now we have one array of tasks per chunk. And in every chunk, your workers would all be working on the same array, but they'd get a different pre-allocated section of that array to work on. These two are pretty much same shit, different pile. But now what we're going to do is we're going to keep the same data arrangement we had previously. We set this whole thing up so that we could compare to the next approach. So we're going to have the same setup where we have arrays. We're going to have a vector of chunk arrays. Each array is just a number of tasks. But now, instead of giving each worker a fixed contiguous section of the chunk array, every worker is going to pull tasks off of the next unprocessed task from the top of this array. So when you start off, worker 1 is going to get, the first task. Worker 2 is going to get the second task. The third task goes here. The fourth task goes here. And then when let's say worker 2 finishes its task first, it had a small one. So then it's going to take this task here and start working on that one. And then maybe worker 1 gets this task, and then maybe worker 4 gets this task, so on and so forth. So essentially what we're going to be doing is in our master control, it is going to keep track of a pointer or an index to the next task to be processed. And when the worker is done its current task, it's going to ask master, give me another task, and master will take the one that it's pointing to and say, here's your one, and then it'll increment that pointer to point to the next one. There you go. So it's a very simple approach. It's going to be very easy to implement, but it's going to show us some interesting things, I hope. It'll be a good journey, so stick along for that. Now, before we jump right into creating the queued approach, I just want to reorganize this code just a little bit, because now we're going to have basically two sets of code that do almost the same thing, but do it in a different way. So I don't want to jam everything into this main.cpp. It's starting to get a little fat. So what we're going to do, we're going to pull out common stuff like these constants and like task. We're going to pull those out into their own separate files. And we're going to pull out stuff like master control worker and do experiment. We're going to pull those out into their own files, and they're all going to be in separate namespaces. So we'll have two master controls, but one will be under the namespace for pre-allocated, and another one will be under the namespace queue for queued. And you'll see how it works. I'm just going to organize things, separate them out into different files, and clean things up a little bit. And here, this processing of the command line options, it's not very good, because if we put this option anywhere but in position 1, it won't be recognized. So I'm going to actually pull in a library for command line options, and we'll use that. But I'm not going to do all that code monkeying on screen. It'll take too long. So I'm just going to cut to the changes. And if you're interested, you can look at the Git history to see a little more granular flow history of what changes were made. All right, so let's take a whirlwind tour of all the changes that were made here. You can see main has become very small. I pulled everything out of main into a bunch of different files here. So I'm using this library called Popple for parsing the command line, and you can find it on GitHub. The link is right there. And we can just define different switches. I define a switch for stacked and even, so you can choose how your data set is generated on the command line. And then we call do experiment. You can see do experiment is now in its own namespace here. But I pulled a bunch of things out. Constants are now all in their own file here, and that'll be included in a bunch of places. Task header includes the definition of the task structure definition of a data set using, and definition of all the different generating functions. Timing includes the definition of chunk timing info and the function pulled out for writing the CSV. What else do we have? Constants, task, timing. Okay, so that's all the common stuff pulled out. Here is the code basically from the last video. Just copy and pasted it in here, put it in its own namespace. And I also, I factored out the right CSV stuff. I also factored out, as you can see here, the selection of the data set that's not in here now. The data set that it uses is just getting passed in, and that is selected in main, as I've shown. So that is all the reorganization. Then I just took, wait a minute, where is it? Queued. I just took this code and I copy pasted it into here and put it under a different namespace. And here's where we're going to be, wait, no. Queued is the one we're creating. Yeah. So I took the pre-assigned one, I copy and pasted it into here. And now we have to modify this code to use a queue instead of pre-allocating sections of the array. Now, before each worker was given a span to work on, and it just looped through its span, but now that is going to have to be managed by the master control, which is going to just give pointers to the next task. The workers will just ask for a task. So workers are no longer going to be managing the span. So we got to put a span into our master control, and we'll call this the current chunk that is being worked on. So this will hold the entire chunk, and then we need a pointer, or in this case we'll use an index to the next chunk to be processed, and we'll just initially set that to 0. Alright, so the master control is going to initialize, it's going to start with the mutex locked, which is fine. Now the mechanism for having a worker signal that it's done and for having a worker wait, that'll be the same, but we need a couple functions. First of all, we need a function to set the current chunk that'll it is being worked on. So we're going to pass in a chunk, which is just going to be the entire chunk array, but we'll take it in as a span because span is just more flexible. And what we want to do is we initialize index to 0, saying that we're going to start at the top of that chunk, and we are going to say, okay, so the current chunk is equal to the chunk that was passed in. And there you go, we have the current chunk. Now, what we're going to do is when workers are working, they are going to ask for a task. They're going to say, give me a task, give me the next task to be done. So we'll return that as a pointer. Now this guest task is doing two things. It's going to return a pointer to the task to be processed, but it also has to increment the index here, so that the next time we call get task, a different worker will get a different task. And we also have to check if we are at the end. If there are no tasks left, we should return a null pointer saying that there's nothing left, you're done here. So how do we do that? Well, let's go const auto I is equal to idx plus plus. So this will store the current value of idx into I and then increment by 1. So once we have that value captured, we're going to check to see if that is past the end of the chunk. Because if it's past the end of the chunk, we just want to return null pointer. We obviously don't want to dereference that. That would be a bad idea. Otherwise, very simple, we just return the address of the current chunk at I. And that'll get us a pointer to a task that can be processed. And there you have it. That is all that needs to be done to master control. It is now perfectly set up to work as a queue of tasks. So now the workers are going to need a little bit more work. They need master. Okay, so this part is fine. Set job is no longer a thing because you don't set jobs on workers. Workers ask the master for their next task. So clearly, if we get rid of that set job function, we should also get rid of this variable, the member variable, the input, because it's not needed anymore. Work time, number of heavy items processed, dying, yeah. So let's add another flag in here, and we will call that one working, and that is equal to false. All right, so now we have working. Okay, so this obviously is not necessary anymore. What we'll do is when we have finished processing data. There's no data left to process in the current chunk. We'll set working equal to false. Okay, so here we can see that our condition is if input is not empty or if we're dying. We should say here, if we are working or we are dying, we should wake up. So that's this set here. Now the only real big change to be made is in process data, because now we don't have the input anymore. So how do we process our data? Well, we can do auto p. Now let me think here. I'm thinking maybe like while auto p task is equal to p master pointer to get task. So as long as we're getting a non-null task, we should then do task process. Is that happening? Identifier task is undefined. P task, right? Because it's a pointer now. P task process and P task heavy. And so basically we don't have to really change the structure of this. We barely have to change it in order to satisfy the new conditions. Now we have this Boolean flag here working, and we know where it's set to false. It's when we're done processing data. But where is it set to true? We actually need a way of setting that externally. So we'll do void start work. And we are going to set it under a lock, just like you would set. It's basically the same as dying, only we are going to set working equal to true. So there you go. Externally, when we're ready to start a new chunk, we just call start work on each of our worker threads, and they would go to town grabbing tasks from the master until there's no tasks left to grab. And there you go. I think that should probably work. Compiler isn't complaining too hard. Now we just have to change the experiment in order to fix it. So the only code that really needs to change is this stuff in here, right? Because now we're not working on subsets. We're just going to set current chunk on the master control. So mctrl.set chunk, and we'll just pass that the chunk from our ranged base 4. Very clean, very simple. And then for each auto p worker in worker pointers, for each of our workers, we have to tell them now to start work. Now that we have the chunk set on the master control, they are able to start getting tasks from the master. And then we just wait for all the workers to say that they're done. And then we go down here and we do our measurement stuff. Same as usual. And this stuff here is all the same. So there we have it. We have created our queue-based approach. Hopefully there are no bugs. If so, that'll be a problem. Now we should add a way of setting that from the command line. I'm just going to add a new switch in here. We'll call this switch queued. Use queued approach. All right, so now if I do it like this, I should go like if queued pointer to is set, then we'll just do it. Else we'll do this one here. And okay, so we have pre-assigned, we have queued. So now we just have to call, do that. We'll call this one QUE, do experiment. There you go. So now if we set the queued on our command line, let's add a few more options in here. Let's go QUE, UED, and let's add another one in here that is even. So we'll turn that one off. There we go. Turn them all off. So now we'll have a random data set that is not running on our queued approach. And let's just try this out. So we'll build. Going to run with 0 options set. Processing took 1.74 seconds. So that should be a random data set on pre-assigned workload. Now let's turn it with queued 1.67. So it shows a little bit faster. It's not an enormous improvement, but it is a bit of an improvement. But now let's take a look at what it is in the worst case when we have a stacked data set. So we're going to run it not queued with a stacked data set. And it is going to tell us that it takes quite a bit longer, 4.33 seconds. Now with the queued approach, and we should see, 1.68, so about the same whether the data set was stacked or not, which is what you should expect, because the queued approach doesn't care about the order of your data. As long as there are work items to be done, they will be assigned to a worker. You won't have any workers standing there with their thumb up their butt. But there's one more thing that an acute observer might have picked up on here. Let's run queued again. I'll just turn off stacked, not that it matters. 6557. Let's run it again. 5678. Oh, that's a problem. Looks like we're no longer getting the same result every time we run the program. Now, bonus points if you can figure out why that is without me telling you. So the problem is in this line right here. It seems innocuous enough, but this is a catastrophe waiting to happen. The operation that's happening here is, well, first we're loading the value stored in the memory for this variable into a local variable I, and then we're incrementing this value. But those are two separate operations, and one thread might execute the first part of that, and then another thread might execute the first part before the first thread was able to execute the second part, and that causes a problem. Let's just break it down because it's very important. So there are a bunch of permutations that could go on for this set of operations for two threads, but we're just going to look at two permutations. So the first one is the happy case, the case where things go as we would hope them to go. And that is, okay, we load the value in, this is I dx, if that isn't obvious. We load that value. So now I is equal to 5. And then we increment this, so now it's 6. Then thread 2 is going to load the value, I is equal to 6. And we increment that, and it is now 7. Yeah, beautiful. And everyone's happy. The next thing that grabs is going to get, I7. And they're all going to work on different tasks. Everyone is happy. Now, what happens in the pathological case? Well, thread 1 grabs its value, I is equal to 5. So far, so good. Then thread 2 captures the value, I is equal to 5. Uh-oh, these two threads are now working on the same thing. Now thread 1 increments, and it is 6, and then thread 2 increments, and it is 7. So who's working on 6? Nobody. And that's just one example of the way that things could go wrong. I'm sure there are others you could cook up, but the end result here is that the same processing is not going to be happening every time. So what to do? Well, I mean, I think the solution is pretty obvious. We need mutual exclusion to protect this axis here. We got to make this operation of loading and incrementing, we need to make it indivisible, atomic, so that no thread can interpose in between those two steps. And of course, we know how to do that. We do std lock guard. Put a lock, let's just call it LCK, on our mutex. And we can use the same mutex that we use for other synchronization here, because it's not being, at this point here, it's not being used for other stuff as well. So it should be fine. So we grab the mutex. When we want to get a task, we grab that mutex. And then we do this operation. And if other workers call get task at the same time, well, they just have to wait. And that's the end of that. Okay. So now if we do this, we see 1.66 seconds, 8145. And let's run it again. 1.65, 8145. All right, so we have stabilized our result. We no longer have a race condition, which is, that's a good thing. But actually, counterintuitively, our processing time went down. So normally, you would expect to, when you add synchronization into your code, it would slow down your code a little bit because there'd be contention on the lock. And if a thread tries to lock the mutex when it's already locked, the thread gets stalled. It goes up to the operating system scheduler, and it's just generally, it's not a very fast process when you have contention on the mutex. But you can see here, we actually go faster. And I believe the reason why we're getting a little bit faster is because we're removing perhaps some cases where the same two threads process the same data. So duplicate processing of some data item. I think that might be the reason, although I'm not 100% sure, because if you look at this scenario here, yeah, the two threads process the same item, but then one item seems to get skipped, if my analysis is correct here. But I'm just guessing at it at this point. But the end result here, I think the big takeaway here, and the thing that I really want to nail home, is that some people don't understand the relative magnitudes of what things cost in processing, and they try to do optimizations when they're not really optimizations and they're just wasting their time. And in this situation, it's very clear that adding a lock is not slowing us down any appreciable amount. So if you were to try to optimize this further by using lock-free programming, you'd probably be wasting your time in this scenario here. And that is a very common case in the real world. The magnitude of the operations that we're doing, if we look at the constants, the size of our heavy iterations and our light iterations, fairly heavy operations that we're working with here. And so the cost of locking is insignificant compared to that. And so you shouldn't waste your time trying to prematurely optimize here. That's the main takeaway that I want to put here, because a lot of people, they're just like, I never use mutexes. Why would I ever use a mutex? And the reason is because it generally generates less bugs in your code, and it's just a more solid and easier to understand solution. So looking at the CSV, the story is, it's pretty clear. Here's the situation we had with the pre-assigned. We can see all the heavy work is being done on worker 0. All the rest of them have 0 heavies. And you look at the idle time of worker 0, it has no idle time. It's always working. You can sleep when you're dead, is basically its motto. Whereas with the other workers, they're working 7 milliseconds, and then they're taking 38 milliseconds break. So they're wasting a lot of time. In fact, total idle time exceeds the total time it takes to process the entire chunk. Now, when we do the queued, right away we can see here, idle time for all these guys is basically on the same order now. They're each taking more or less around the same amount of idle time, maybe within one order of magnitude, which is pretty good. And there's a lot more distribution of heavy work items. But even if the distribution is bad, like we see here, this unit here, thread 2, got a lot less heavy items than the other threads. That's just the luck of the draw. When it pulled items off the task, it just got a lot fewer items. But its idle time was not any greater than the other guys, because it probably just ended up doing more light items to make up for it. So I didn't actually put this in here but it would be interesting, and you could probably get an insight if you also added a column for just total number of items processed, because now they're not all guaranteed to process the same amount of items. I bet you any thread worker that you see that has fewer heavy items will probably have more light items processed. So that's just my my intuition there. But you can see, better distribution, lot less idle time here. Yeah, look, the total idle time now is like on the order of, a few tens of microseconds, about 50 microseconds. Whereas here, the total idle time was 100 milliseconds. So we're like, I don't know, like 10, let me think here, 2,000 times less time waste going on here. 2,000 times. That's pretty good. That's a pretty good improvement of a metric there. But there you have it. Now, these results that we achieved, they were achieved with a specific set of parameters here. If we were to change the size of tasks, we might get a little bit different outcome in terms of performance. And that's what I want to look at in the next video. In the next video, we're going to look at the case where your tasks are much smaller. You can't group tasks together into big chunks of work. Maybe they have to be fine granular. And how does that affect the overhead of our thread synchronization? And we're going to do a little, we're going to dip our toes a little bit looking at the disassembly, and we're going to play a little bit, just a sneak peek of atomics in that video. So that will be the next video. Until then, thanks for watching. Hope you enjoyed this one. If you did, click the like button, and I will see you soon with some more C++ multithreading.